Yet another problem we're going to model in Desmos. I'm not going to go through the whole calculation here, but the other day in class we did something called the conical pendulum. So I just put a mass on a string here and basically gave it a push so that it went around in a circle tracing out a cone. And when it does that, we measured the period and we measured the length of this string, and we did it for a fairly small angle. But if you want to see the calculation or the derivation, I'm going to scroll. Now, I'm really interested in the result here. Period is 2 pi, the square root of the length of the string over the acceleration due to gravity times the square root of the cosine of theta. Now, for a regular pendulum, there's no cosine of theta term. It's just the rest. But for a conical pendulum, there is a slight dependence on the angle. At low angles, it's slight, and as you get to bigger angles, it's a much bigger dependence. So this is a fun thing to do in Desmos, like a lot of things. So first, let's look at some data that my class took. So, we were crunched for time, so we only had 5 data points. So we had 5 different lengths. And what I did is I threw stopwatches out at the room, mostly to people, and they timed them. And I just had them call them all out, and then we averaged them. And those are the times when you divide by 10, that gives you the period. And those are the periods I used that I plotted. So we're going to do a fit that really only has 5 data points, but those times are actually averages of about 6 to 12 time measurements. So I took this data and I copied and pasted it at this Desmos. So if you want to play along, this is the code. You go to desmos.com/calculator and then this business. Ignore this for now. This is the theoretical function. Well, I guess I could do it. So if I was to actually type in g equals and put g equals 9.81, and I was to toggle off my fit function and toggle off my data for a minute, you could graph that, and that's going to be the theoretical equation. And we can play with things like angle, see how the angle affects that. Again, for small angles, it doesn't make much of a difference, but for big angles, it starts to make a huge difference. I'm going to put that to 0 for a minute. This is a little trick I like to do where instead of graphing it versus x directly, where x is the length of the pendulum, I use L in the function to use x. But if I wanted to know the actual, add an actual value, an actual length, say, of 2 meters, then what happens is this formula condenses down to a value. But if I want it to graph, I make that L equals x, where x is the generic x variable. But I want to do a fit function. So I want to actually use this to see if I can measure g using a conical pendulum, just because, I don't know, because we can. So I'm going to toggle this off, and then I'm going to actually delete this where it says g, because I want to do a fit function where Desmos gives us g. So I'm going to toggle this back on. There's our data, and it looks kind of linear to the naked eye, but closer inspection, it's not quite linear. It's closer to what we did a second ago. So let me make the a 0. And again, when we enter the same function. T1 is what I used for the y variable in the table. L1 is what I used for the x variable. Cosine A is the angle, that's a parameter there. And g. Now g isn't equal to anything, so Desmos is going to know that it's trying to find a value for g. And instead of equals, you have to use this tilde, this squiggle in the upper left of your keyboard. And when you do that, you get a g. Well, first of all, if I plot it, you can see just, similar to Excel, it'll draw it on there, that equation. But look at the value of g, 10.097. At first you're like, yeah, yay, that's almost g. But then you're kind of like, g's really 9.81. Like, that's not as satisfying. But if you think about it, this is a conical pendulum, and the angle does matter. So if we increase this angle, even just a little bit here, to say something closer to 10 degrees, we're down to 9.94. If you go to 15 degrees, you're already down to 9.79. Now, it's not a perfect experiment. I just sort of gave it a push. But when we make this angle around there, which is around where we're using, we get much closer to to 9.8. And it's fun to talk about, like, well, how can we do a better experiment? And you know, physics is fun. But here's another example where you're graphing a nonlinear relationship. Now, you could, of course, graph it instead of versus this. You could graph it versus cosine of theta or something. You can linearize it is basically what I'm trying to say, so that the g gets pulled out. So yeah, yet another thing that we have managed to do a fit function in Desmos.